Right, so we're on the second class of the signal transducers or signal cascade pathways. These are the receptor tyrosine kinases, the RTKs. And so what do you suppose, if we just do a quick review, once again, I suggest like somewhere in the front of your notes or whatever, you just right now start having a list, an ongoing list that helps for studying on the classes of enzymes. First of all, what's the ending to let you know it's an enzyme? ACE, okay? So receptor tyrosine kinases means it belongs in the family of kinases. And what do kinases do? They transfer phosphate groups using ATP or GTP. I think in theory it's supposed to be any of the NTPs, but those are the two Bs. Okay, like vast majority is ATP. You just had to have a guess. You put down ATP as the other one, and then transfer is correct, and if not, it's a GTP. Okay, but ATP and GTP. Whereas if it transfers a phosphate group and it doesn't utilize ATP or GTP, what are those enzymes called? Phosphorylases. Okay, phosphorylases, and then we have the third that sounds a lot like it. It's called the phosphatase. Does anyone know what a phosphatase does? It's also to do with phosphate. Typically, what a phosphatase does is it removes a phosphate from something in the form of inorganic phosphate. And so, let me just write that down so that way you can see what I mean. So it's called a phosphatase. And so let's say, for example, we had, I'm going to call it substrate, that has a phosphate on it. That substrate's phosphatase, what it would do is it would just have the substrate plus an inorganic phosphate as a product, where it just removes the phosphate. Okay, so that's a phosphatase. Phosphorylase would be like almost the inverse of that. Like you flip it around, it'd be phosphorus. Sometimes enzyme metabolic pathways are named further backwards, because that's how it was discovered, or who knows. But whereas a kinase always utilizes an NTP, like ATP, GTP. So this right here, the reason why we put this is RTKs, that you know, these are kinases, there's going to be ATP and or GTP involved. And what do you suppose is being, and my old boss hated it when I say kinase, but you know, if I say kinase, you know exactly. And it's so much easier than saying, what do you suppose a phosphate group is being transferred from an ATP to, the substrate. So what do you suppose is being kinased for the receptor tyrosine kinases? Tyrosine. Okay, and so we know that tyrosine is used. Okay, so that's why. And the receptor, of course, is just the receptor. So I really liked this figure, and so like I said, that's my little outline. It just lets you know that, of course, it doesn't tell you the whole scheme of things. We've already covered the GPCRs, which was G protein coupled receptor, not the generalized polymerase chain reaction. Okay, it was on the quiz. And so there's receptor tyrosine kinase. And remember, the very first event, regardless of what happens, is the same for the first two. Okay, there is a pseudo exception. But what was the very first thing when we did the epinephrine, adrenaline pathway? What was the very first thing that had to happen even before anything? Binding. And the same thing happens here. So many times you're going to be doing comparison and either comparing and contrasting how things are the same or how they're different. The way that these are the same is you have an external signal that binds to an external receptor on the cell, okay, that causes some type of change on the inside. Right. So I use it because there's only so much space integration. I especially in biochemistry too, I talk about Moses in the Holy Land a lot. And so for these, just like with epinephrine's like Moses in the Holy Land, you can see the Holy Land, but it cannot enter in. So same thing here. Insulin is a textbook example that we use for RTKs. Insulin cannot enter, or does not enter into the cell. Okay. And now later, assuming that we have enough time at the end of the semester to go over hormone pathways and hormone regulations, metabolic pathways, we'll actually go over the entire insulin pathway, about how insulin, since it's so important, how insulin is made and how it's released and all this kind of stuff. But I don't think it's really covered. I don't cover it in this chapter because normally this is a chapter for for Biochem 1, and we cover hormone therapy later on. So so that's the biggie. You have to have something, so they are going to be plasma membrane receptors. They have to have one end on the inside, they have to have a side on the inside, a side on the outside. They transverse it, but they do, remember transduce is just a fancy word meaning transmitter. You alter signals differently. They do not have a GPCR. I mean, they don't have a G protein in that sense. Now we're going to see there may be G proteins further down the cascade. There is for insulin, but the actual insulin receptor, the RTK portion of it, is not a G protein. Okay. Now, one other way that it's different is if. Will this let me change it? Oh, good, it does. Is if I draw. Remember that's my generic cell membrane. Okay, and remember for the, what was I going to say? The GPCR, for like epinephrine, we had this, and then there was the G protein was here, and then there were other proteins, and so on and so forth. So we had the binding here, which affected this protein, which affected that protein. One way that's a little different here also is their active site is the same protein, but it's on the other side. And so for it, I'm going to draw in a couple of what's supposed to be phosphate, the lipid backbone. For it, we have the insulin binding here. But what happens is these usually are at least dimers. Remember, that means there's at least two proteins, if not more, where this one will phosphorylate its partner and so on and so forth. They do what's called autophosphorylation. They phosphorylate themselves. Another one is epidermal growth factor.
But it has to start from an external?
Yes, insulin does not enter in. Moses not all the way in. It binds here. Whenever it does, it activates the receptor. And the receptor, I always say it's like, you scratch my back, I scratch yours kind of thing. They autophosphorylate. When the insulin comes and binds, this one goes here, and they put the phosphate groups on their other side. So that's what the kinasing is. And so one thing we've already talked about what that means once again they transfer phosphate at the expense, it does require energy. That energy is at the expense of ATP or GTP, but from here it's ATP. So the example that we're going to be using is insulin. Okay. And, cell biochemistry, especially cell and molecular biologists, they love, their acronyms and everything. So INSR is an insulin receptor, which that makes sense. The reason why I point this out, we have a couple, there's some that I don't even remember, I just remember their acronyms, but you're going to see they have some that are just atrocious, but coming up. Okay, so this is the INSR, the insulin receptor system for RTK. All right, so we have insulin, which it is a hormone, since we've already talked about. I've already mentioned, but I've repeated, does it actually go into the cell? No, it doesn't. What does insulin regulate? Glucose, okay, blood glucose. Now, does insulin kick in whenever your blood sugar is high or whenever it's low? High. Okay, what's the opposite? What's its antagonist or its antithesis? Not glycogen. That's the one that I know I usually get. It sounds a lot like glycogen, stored sugar. Glucagon. I know. It kind of even sounds like a sinister name, like a villain. Superman and Lex Luthor. I don't know. I should say it's a villain. You need glucagon too. Okay, because otherwise you die. So, but yeah, the glucagon is its opposite. You want to think that way. It's bifurcated. So the bifurcation, remember we talked about that, means it's split into two. Think of it like a snake has a bifurcated tongue. The law of bifurcation in forensic science means, it's called the fallacy of bifurcation. It's when you try to give a complex thing, either yes or no answer. This means it's split into two. For insulin, there's what's called the MAPK cascade portion, and there's the PIP3. Okay. Right, and that's for phosphatidyl and inositol triphosphate. So that's why PIP3 is just easier. We'll talk a little bit about PIP3. PIP3 uses another kinase. Remember we had epinephrine had the second messenger for CAM, cyclic AMP. Cyclic AMP turned on what enzyme? PKA. Insulin, if it does this branch, I don't know why they call it beef. You're gonna find there's a PKC, which makes sense because calcium is its is its second messenger. I don't know. I think that it was probably this one was, and they said we have an A, we have a C. Why don't they call it a P or an I or something? I don't know. They call it B. But protein kinase B is the one that's involved in that. But the K here is kinase. Okay, the MAPK, yes, and you're going to see what I mean in just a moment. Okay, so it's bifurcated. All right, this is 1/2.
Oh my gosh.
Yes. All right, so where the bifurcation occurs is right here at the binding unit. So we can see there's binding, there's autophosphorylation that occurred. That's the IRS. How about this on the thing instead of walking before? That's the IRS. I'm sorry, that's the INSR. INSR. This is IRS. This is the good IRS. But bifurcation occurs. You don't see it is right at this point. You know, you can go over to the PIP3 cascade, and I'll show what that looks like in a moment. I'm actually here. Let me just go to this next one because it tells you. I want you to know the major players. As I mentioned, yeah.
What does the S stand in the IRS?
I don't know.
Okay.
That's one of the ones I don't remember often. I wanted to say, is it insulin responsive signaling? I don't know.
Okay.
INS is insulin.
Right.
The RS, it may be insulin responsive system.
Okay.
So, yes. Some of them, just like I don't know, GRAB2. They call it GRAB2. I have no earthly idea what that means. RAS, I don't think actually has a name. I mean, I think it's RAS because it's short for something else. Okay? That's why I said they love their, and some of them are named after phenotypes that were given to yeast or bacteria or something, and so then it's historical. That's how we have like the fuzzy gene, and there's a wuzzy gene. Because they said fuzzy and wuzzy was a bear. Yeah, so they, stupid things. Okay. So these are the ones I want you to know. And this is, like I said, it's on the notes. And this comes from the book. I'm walking through it. And I want you to understand what these family names mean. Because this one, the hardest part for me is, and hopefully it makes some sense later on, is it actually goes backwards. Like the way they get their naming is backwards. Like you actually start with the end product and you work your way up. Which, well, let's just know what that means in a moment. First, I'm going to take you through what happens whenever we're doing the MAP. This is called the MAP kinase pathway portion of insulin. Insulin binds, it causes autophosphorylation of the tyrosines. This in turn, because these are kinases, so at the expense of ATP, they are going to then phosphorylate IRS. Okay, and so IRS, once again, this is the good IRS. Once it's phosphorylated, it's activated, and it in turn activates this whole chain. And so you have the link, there's GRAB2, there's SOS, which SOS is technically the family that some of these that maybe even in your papers that you're supposed to be working on. If you see something that's called a GEF, G-E-F, that stands for guanosine nucleotide exchange factor. So all it means is those are the kind of things, those are like G proteins. Oh, those are like G proteins that, how do I get that off now? I don't know how to, there we go. Yeah.
So in the picture, the little orange IRS one, does that mean that it's like kind of further in the membrane and then it like?
It associates with the membrane, so it's phosphorylated.
Okay.
When it's phosphorylated, it then, that's when it's activated, it leaves to go on to do this whole cascade. Okay. Then we have GRAB2 and SOS, which those are just ancillary or auxiliary proteins to help ultimately activate RAS. And RAS is the one that we're going to, and for those that are in chemistry cancer, we're going to talk a lot about RAS. Because RAS is implicated in so many different types of cancers, and I'm going to say like certain types of colon cancers, 90% or more is due to single mutation in RAS. So, all right. So we're going to spend some more time later on with RAS. Then this is where we get to the actual MAP kinases. So far we haven't gotten to the MAP kinase portion. And why do I keep doing the wrong one? Go back here. This is where I'm going to actually see there are all these series of enzymes, and all that they do are phosphorylate each other. Okay, so if you notice, we have here RAS activates RAF1, RAF1 then takes MEK and phosphorylates MEK, which does ERK, which phosphorylates and activates ERK. ERK goes on, and ERK then phosphorylates, and you ultimately get the transcription of genes in the nucleus. Okay, so the MAP stands for mitogen activation protein, okay, which it has to do, it was one of the first proteins that was discovered that had to do with transcription. Okay. So what happens here, now we're going to work backwards. This was the gene, okay, that got protonated. So these are the mitogens. These proteins got phosphorylated to be active. So the enzyme that immediately did it, ERK here, is called a MAP kinase. Okay, because it was one of the first ones that was discovered. It was discovered that, for example, ALK1 had to be phosphorylated for transcription to occur. Well, whenever they found the enzyme that phosphorylated, they said, this is a MAP kinase enzyme. Okay, it's phosphorylated, it transfers, there's a phosphate that gets added onto it, and everything's good and fine and dandy. But then, whenever they started studying this, lo and behold, they found there's MEK. Well, MEK is also an enzyme, it's a kinase, and it kinases ERK. So what could we name it? So they said, how amazing scientists can be, cell biologists, some molecular biologists. They named it, that's a MAP kinase, because it kinases MAP kinases. Well, lo and behold, they discovered RAF. RAF1 is also a kinase that it kinases MEK, which kinases ERK, which kinases ALK. So they said, what class, and there are other enzymes that are related, and they said, what can we call that? Well, since that's an enzyme that kinases the MAP kinase, we'll call it the MAP kinase. Or sometimes they call it MAP3K. That's why I say it's ridiculous. No, I'm not going to call it that. Okay. So, that's why I say these are historical artifacts, but the one that's closest to the DNA is the lowest in the Ks. Then it's each enzyme. So that's why if you start to understand the way the enzymes get their names, it starts to make some sense. So for example, this MAP kinase is the one that literally does, literally phosphorylates the MAP proteins. This one is the one that phosphorylates the one that only has 1 K. This one is the one that phosphorylates the one that had 2 K, that phosphorylates the one that had 1 K, so on and so forth. So that's why if we work backwards, here, if these were the maps, ERK would be MAP K, because it was the one that phosphorylated here. MEK would be the MAP KK, because it did ERK. RAF is the MAP KK, 3K. We'll go with that, MAP 3K. All right, so RAS does not do that. RAS, we'll see what RAS does in a moment. It's the one that helps, really is a checkpoint for at this point. Okay?
Sorry. So when you say you want us to know the major players, do you want us to know them as the MAPKs, or do you want us to know them as the ERK, MEK, RAF?
No, not ERK, MEK, RAF, because you're going to find out that, especially, this was first discovered in insulin.
Oh,
but this insulin is not alone to insulin, and those proteins have different names. Okay, but they are still in that same family, being a MAPK.
And they still all go that direction as far as the case.
Can you say that one more time? So MAPK is ERK.
So that's why if we start, I always because for me to start this, here's the DNA that got transcribed. So the MAP proteins were the ones that did that.
Okay.
And see, it got phosphorylated, and it had to get phosphorylated by the kinase, so therefore ERK is MAPK. The ERK, in order for it to be active, it had to be phosphorylated. See, because it was before, it was nothing. I shouldn't say nothing. It was inactive. And so what phosphorylated it was MAPKK. And see, MEK was not phosphorylated before, and it was inactive, and it got phosphorylated by RAF1, so it was a MAP3K. I did it correctly that time. And so, whereas RAS is the one that, like I said, it's the checkpoint. It's not what started it, but it's the one that keeps this under tight control in that sense. And we'll see how that does in a moment. One other thing to point out about RAS is if you notice, it's got this little tail thing. It's called a farnesylation. It has a farnesyl group. Farnesyl groups are lipids. But they're not fatty acids because they don't even have a carboxylic acid end. Each farnesyl group has 15 carbons. So they are extremely hydrophobic. In fact, they're made of something called an isoprene units. Very, very hydrophobic. They get added on farnesyl group, and then, once again, cell biology sometimes I think were the ire of my graduate school and medical school. So farnesyl is an old term comes for 15 carbons. For 10, it's called geranyl, G-E-R-A-N-Y-L. Well, one thing to notice is 10 doesn't really get used very often for making these groups, but 20 does. So since they said, okay, since 10 plus 10 is equal to 20, we'll call it geranyl. So it's this really long name for geranyl. It's even called gerynylation, which is hard to say. That means it's got 20 carbons. Farnesyl is a lot easier because farnesyl group probably happens more often than. But that gets added. It's a post-translational modification. RAS, when it's first made itself by the ribosome, it doesn't have that farnesyl group. There's an enzyme called farnesyl transferase. That's another class of enzymes to be putting down. That one's an easy one to know. Transferase. Farnesyl transferase are groups of enzymes that add the farnesyl group to these proteins. What happens here is if this little farnesyl group doesn't get added on, RAS can never be activated. It has to be in the membrane for this to work. Okay, and so that's why there are lots of, you can imagine now, there are lots of cancer drugs that look at this kind of pathway in general, because you can modify the transcription, how much is transcribed. Because since cancer many times is due to unregulated transcription of bad genes, I shouldn't say bad genes, genes that shouldn't be transcribed. Then if you can somehow modify this pathway, then you can probably downregulate it as a possible chemotherapy drug.
So RAS gets farnesylated.
Yes, and yeah. So I'll actually have a picture of RAS. I don't know if it's in the very next one or not because I didn't bring up my other. Okay. Yes, this is RAS. So I didn't have it next here. Let me make it a little smaller so we can see it all. First thing you should note, RAS itself is a G protein. It's just not part of GPCR. Because that's a G protein coupled receptor. That was when the G protein was coupled to the actual receptor. Remember, it's just called a G protein because it binds GTP and GDP. It's not really big. RAS is really tiny. It's a monomer. It's not this major thing. I don't think that we have a farnesyl group on this one. They don't have a crystallized farnesyl group on it. But it has to have that farnesyl group, and I can't click on that because this is a PDF that's been put in the program, but I did check to see if that link was still active or not for today's class. But farnesyl groups get anchored to one end or the other. I can't remember which end it is. And once again, it's 15 carbons. It has a double bond with some alkenes to it. And so it's really hydrophobic, and so it gets inserted into the membrane. This is a little anchor helps hold RAS in place. RAS is really tiny. It binds, we can see the GTP here. And depending upon whether it's GTP or GDP, is whether or not RAS is active or inactive.
So RAS once it's farnesylated is hydrophobic, or it's
right. Yeah, it makes it even more hydrophobic. I mean, there are parts that are hydrophobic just naturally, but it's that those tails, those farnesyl tails or geranyl tails, those are so hydrophobic. That means that's a surefire sign that protein has to be in the membrane or in a membrane. It could be in the membrane, something like that, because you can't have that out in an aqueous environment. Those are 15 carbons stuck out in the end like a little tail, and so they're not going to be happy. Very, very hydrophobic. Okay, so that doesn't. I so wish I could click on that to give you the actual percentage that match. I know one type of and there are 3 versions of RAS. I know one's called HRAS. Its name is Harvey. I'm assuming that was their last name. I don't know, but it's called HRAS. And there's another version that's called KRAS, which is for Kirsten. That's their first or last name. And I think there's an NRAS, but the H and K RAS are the two that are the most prevalent. And there's a specific point mutation in one of those, I can't remember which one it is, that causes over 90% of colon cancers. They're also involved in pancreatic cancers, and it's really a lot of research is done in RAS. So it's this seemingly innocuous tiny thing. And then I've got a little cartoon coming in to show you like how GTP or GDP, how it actually dictates whether or not it's active or inactive. It's really cool. But it activates ultimately the MAP3K, which goes to MAP2K, MAP3, and ultimately does that. So that's why it's kind of like a checkpoint. Oh, there's a domain, this one's not, that you see a lot of times that you find out for the signaling structuring pathways. They're called circ domains, circumology domains, just based off of the original protein that it was. But anytime you see that, that usually means it's a tyrosine kinase. There are lots of different types of tyrosine kinases. So that's just something that you'll see. It's called an SH2 or circ domain. All right, here, we're not going to look at that one.
Are you going to have the, unboxed?
Yes. Mm-hmm.
Okay.
Yeah, I just didn't want to do it beforehand. Okay. All right, so these are just, I just wanted to put this up to let you know that there are lots of different types of these domains that you see over and over again. There's more than, once again, SH2 and SH3, those are just circ domains, but that just means that they're usually involved for tyrosine kinases. We have here, you can see a tyrosine kinase domain. Okay, we can have a phosphatase domain, which we already taught. That means it removes phosphates, because we need those enzymes as well. There's lots of these different types, and these are just things that you may come across in your own papers or anything like that, or especially those in cancer, some of the things that you're talking about. You may maybe all of a sudden talk about circ domain or tyrosine kinases or phosphatases. Okay, I wanted to really focus on this part right here. Okay, RAS. This is how RAS, like, is really, really oversimplification, but I think it's really cool. So RAS actually does have an activity to it for whether or not it's GTP or GDP bound, just like with other G proteins. When it's GTP, so this just shows you, this is the G portion, the nucleotide, it's going to have a ribose sugar, and then it's got 3 phosphates. Since it's got that 3rd phosphate, it actually forms a hydrogen bond to the backbone. Glycine, as you know, can't do hydrogen bonding, but the backbone, it's the backbone interaction with glycine, but it forms an and bonding also to threonine. So it forms these hydrogen bonds that help hold, to me it looks like a little finger in place. Whenever it gets hydrolyzed, and so a GTP gets knocked out and becomes a GDP, so that phosphate, the terminal phosphate is removed, it can't hydrogen bond anymore, and it opens it up. And that's whenever it opens up with GDP bound that it turns on the MAP3K, which turns on MAP2K, MAPK, and ultimately turns on transcription.
So why wouldn't it be able to bond to the second phosphate group?
Because it's just, as if, let's see, I don't think I have a, let's see, it's not very big. Okay, so let me see if I can, you can imagine, maybe, I've got 3 extra fingers, no way. So that's the 3 phosphates, and so those fingers there are perfect length for it to be able to bind. It can't, I can't, double joint enough that it's no longer there, so it can't do hydrogen bonding, so now it's more open. Versus closed, open, closed. So, yeah, just sterically it can't reach. All right, and so last little bit I was going to talk, that was all the one portion of the bifurcation pathway. This is the one that has to do of insulin. This is the second branch. Okay. So the part that they don't, one thing I don't care as much about this one, let me read it. They don't show you the IRS, they don't show you the INSR. It's not here. So if you remember, oh, whoops, I thought I was drawing. It's supposed to be, so insulin binds here and here, it phosphorylates IRS. That IRS is the checkpoint, or that's the point that does that bifurcation. IRS can go towards the MAP kinases, and IRS can go towards the PIP3 pathway. Right. This one, in many ways, it kind of reminds me of the G protein, but it's not a G protein. But it's very similar in the sense that what happened here was the IRS went in, and those that aren't doing, IRS just means that it can go on and activate other proteins. Okay, and one of them that it did was, it did like the GRAB2 and the SOS. One other thing that it does is this enzyme right here, PI3K, which stands for phosphatidyl inositol triphosphate kinase. Okay. And for the life of me, they used, whenever I worked on part of the inositol signaling pathways for one of my rotations at Duke. And we had this little, inositol is a sugar, okay? It's cyclic, it has 6 members. And so if you remember back to organic chemistry, you have the chair conformation. Well, inositol looks kind of like that because one of them is not a carbon, one of them is an oxygen. And it has alcohols that hang off, like so. And I really wish I had this figure, and I've never been able to find it again. Because what they did is they turned it into a little turtle. Like this was, we had a little head, we had a little tail, and all these, and the little legs, and all this kind of stuff. And it was a cute little thing, but it's a little turtle. And the reason why is if you notice, we see like this PIP2, when you see PIP3, you can actually get all the way to what is called IP6 and all these. And that's because every one of those alcohols, and think back to glucose last semester and everything, remember there's all those alcohols on these sugars. Every single one can be phosphorylated. For the inositol signaling pathways, and this is only one of them, there are lots of them, it depends on which of the alcohols are phosphorylated. So there are actually more than one PIP2s, because you could have alcohol number 4 and alcohol number 5 phosphorylated, or you could have 2 and 3 phosphorylated, or for PIP3, maybe it's 3, 4, and 5 phosphorylated. So that's why there's all these, and so it would show you the little phosphates on each of the little parts of the turtle. And so that's why it was just really cute, because you could have the 4 arms, then you could have like 4 legs, because it doesn't have arms, 4 legs and the tail. And so therefore it showed like which ones you pointed out. But what this means that I wanted to point out is it's called PI3K. Because if you notice here, there are 3 phosphates that's on this one. There's the original phospho, and then there's 2 additional ones. PI3K then adds on another one. So it becomes PIP3. PIP3 is what activates protein kinase B. In protein kinase B, actually, the way, and once again, I don't know why they have the B and not an I or something else. But protein kinase B, what it does is it phosphorylates this enzyme right here, okay? And this enzyme is glycogen synthase kinase, okay? Which that's not on there anywhere, so I better write that down for you. It's really important for later on. Glycogen synthase kinase. This is really important because this is the opposite of what we've seen in the past. Always, and so far we've seen when things are phosphorylated, they got activated. This one, when it's phosphorylated, it's actually inactive. Okay, but knowing what you know from your enzyme naming, so we have a kinase. Once again, what do kinases do? They transfer phosphates using ATP and or GTP. Okay. But this one is a synthase. Well, I mean, so what this means, this is the kinase, that activates glycogen synthase. See, that's GS over here. So glycogen synthase is a separate enzyme, but this is the kinase that activates it. What do you suppose synthases do? They synthesize something. And it's really important. So on your list of enzymes, there are two types of things that synthesize things. There's one called a synthase, which is what we see here. So they synthesize something. And then there's another one that I'm just going to tell you right now that you'll probably forget, but it's called a synthetase. And synthetase also synthesize something, but they use ATP or GTP. Once again. So it depends. So right here we know glycogen synthase doesn't require energy for it to make something. So why it's only a synthase. If it required ATP, it'd be called a synthetase. So you just want to do and then what happens is normally, let's say that your blood sugar, so what happens is normally, let's see how can I explain that. So normally, glycogen synthase, if your blood sugar is high, or let's say if blood sugar is high, then you're going to start making insulin. Insulin's going to turn on this pathway. Okay, when insulin turns on this pathway, it's going to inactivate the glycogen synthase kinase. Glycogen synthase kinase, since it's no longer inactive, it's actually going to activate glycogen synthase. So this is once again where phosphorylation does the opposite. So far, every single time we've been talking about phosphorylation, we've been talking about how it turns something on. It can also turn something off, which this should make sense. Anytime we have insulin, that means we have lots and lots of sugar around. We want to be making glycogen. Glycogen stores sugar. So this ultimately, this is the way your body goes and says, okay, now I've got enough for my energy needs. I can start to make glycogen for later long-term storage. And what happens is when insulin levels run low, when glucagon goes up, it's the exact opposite. Glucagon has the opposite effect. So then glucagon does the exact opposite. It's going to make sure that this is dephosphorylated, or phosphatase. Okay, so therefore if this is in phosphatase, it's going to add a phosphate group to the original glycogen synthase. And so therefore, your body won't make the glycogen and start to break it down. Because you need sugar. So glucagon does the exact opposite. Insulin does this way. Okay, so just remember, you have to be able to start to learn how to read these kinds of things. And also, I mean, the good half the battle probably is just recognizing the family names. Okay, synthase means it's synthesizing glycogen. Glycogen synthase kinase, the three just means it's a third isoform. Glycogen synthase kinase means it's adding the phosphate to glycogen synthase. And then we have protein kinase B, of course it has other effects as well. It's like protein kinase A, but one of them has to do with adding the phosphate to glycogen synthase kinase. All right, so I'm going to go ahead and I'll end class with prayer.